Somewhere beyond sight of land, a giant cargo ship is crossing darkness while its main engine has already run for weeks. On shore, switching an engine off feels sensible. Yet aboard this vessel, that simple decision can create a much larger danger. The ship may appear steady and almost motionless, but deep below, engineers keep essential systems warm, circulating, and ready for action. That raises a question most passengers never consider. Why not stop the enormous engine, save fuel, and restart it later? Because at sea, propulsion is more than movement. It supports control, timing, machinery stability, and the ship's escape from danger. And when that power disappears unexpectedly, the consequences can spread from the engine room to every person aboard within moments. To understand why, we must begin with the machine itself, a slow-turning marine engine built specifically for continuous ocean service. Unlike a car engine, it may drive the propeller directly through a shaft, delivering immense torque at remarkably low speed. Around it, pumps move lubricating oil, cooling water, and fuel continuously, keeping temperatures and pressures within carefully controlled operating limits. These supporting machines are not optional accessories. They are vital auxiliaries because the propulsion plant depends on their uninterrupted operation. While the main engine turns, heat, oil flow, cooling, and fuel preparation remain balanced inside a tightly connected mechanical system. Stopping it breaks that balance, forcing the crew to manage temperatures, circulation, and readiness through separate equipment and careful procedures. The longer the shutdown lasts, the more preparation may be required before the engine can safely accept fuel and load again. Engineers must confirm lubrication, cooling, control systems, and starting arrangements, because one overlooked condition can turn a restart into failure. And that is where the real mystery begins, since awakening such a machine requires far more than simply turning a key. Instead, compressed air enters selected cylinders in sequence, forcing enormous pistons downward until the crankshaft begins rotating on its own. Before that happens, engineers must circulate lubricating oil, confirm cooling flow, disengage the turning gear, and check every starting interlock. Only when those conditions are satisfied can fuel enter safely, allowing combustion to replace compressed air and keep the engine turning. But starting air is stored inside pressurized receivers, meaning the crew cannot waste endless attempts on an engine refusing to fire. Each failed attempt reduces the available reserve, while compressors need time and electrical power to rebuild pressure for another controlled start. That makes preparation critical, because cold oil, unsuitable temperatures, insufficient pressure, or an active interlock can delay ignition at the worst moment. Even after ignition, engineers increase speed and load gradually, watching temperatures, pressures, vibration, and exhaust conditions for signs of trouble. A rushed restart can place sudden thermal and mechanical stress on components already weighing many tons and operating within precise clearances. So the greatest danger is not merely whether the engine restarts, but what happens to the ship while propulsion remains unavailable. Without propeller thrust, the vessel begins losing speed, and the flow of water across its rudder steadily becomes weaker and less effective. The steering machinery may still turn the rudder, yet a slowly drifting ship cannot answer helm commands with the same authority. Wind, waves, and currents then begin deciding the vessel's direction, pushing its enormous hull away from the course chosen on the bridge. In open water, that drift may appear manageable, but near traffic lanes, shallow banks, or rocky coastlines, every minute becomes dangerous. Heavy weather raises the stakes further, because maintaining a safe heading often depends on continuous propulsion and enough speed for effective steering. For that reason, keeping the engine available protects more than movement. And the next consequence appears wherever shipping schedules meet enormous costs. Every hour lost at sea can disturb berth reservations, pilot schedules, tug availability, cargo handling, and the vessel's next departure. Because those services are coordinated in advance, one delay can continue spreading through ports, terminals, trucks, warehouses, and customers ashore. A late ship may wait outside port, miss its working window, or increase speed later, consuming more fuel to recover time. Any fuel saved during an unnecessary shutdown can therefore disappear quickly through restarting work, schedule disruption, extra waiting, and operational uncertainty. For ship operators, continuous readiness often offers greater predictability, yet money explains only the most visible part of this decision. The deeper reason emerges when weather deteriorates, because propulsion becomes the captain's strongest tool for maintaining direction and avoiding immediate danger. That danger became real on March 23, 2019, when the cruise ship Viking crossed stormy waters near Norway's Hustadvika coast. Heavy seas exposed insufficient lubricating oil in engine sump tanks, causing pressure losses that shut down generators and produced a complete blackout. With over 1,300 people aboard, the ship lost propulsion and steering, then drifted toward Norway's rocky coastline in heavy seas. The crew transmitted a mayday while rescue helicopters evacuated passengers individually, as engineers struggled below to restore electrical power and propulsion. Before control returned, Viking came within roughly one ship's length of grounding, leaving almost no distance between recovery and catastrophe. Engineers eventually restored sufficient power, but 479 passengers were evacuated by helicopter before the vessel reached shelter with tug assistance. Although Viking used a different propulsion arrangement, its emergency revealed the same truth. At sea, reliable thrust protects every person aboard. Once that thrust disappears, size becomes a weakness, because wind and water can move thousands of tons beyond the bridge's control. Yet ships do stop their main engines safely, but only when location, weather, support systems, and careful preparation make silence manageable. Once securely berthed, the crew can stop the main engine because propulsion is no longer needed to hold the ship's position. Auxiliary generators then supply electricity, while boilers, pumps, cooling circuits, and control systems keep essential shipboard services operating safely throughout the shutdown. With time available, engineers inspect machinery, complete maintenance, restore pressures, and warm the propulsion plant gradually before the ship departs again. That controlled environment explains the title's apparent contradiction. Ships do shut engines down, but they avoid unnecessary silence in open water. The rule is not superstition. It is a practical response to limited restart opportunities, uncertain weather, mechanical stress, and fading control. Modern ships reduce those risks with automatic monitoring, duplicated pumps, emergency generators, alarms, and crews trained to respond before failure spreads. New fuels and hybrid systems may change what powers future vessels, but they do not remove the need for dependable propulsion. Whether the engine burns conventional fuel, methanol, or something cleaner, the bridge still depends on thrust being available when conditions change. That reliability matters far beyond one vessel, because more than 80% of global merchandise trade by volume travels across oceans. Food, clothing, machinery, medicine, and electronics often reach distant countries through ships, whose schedules depend upon engines remaining ready at sea. From the shore, their continuous vibration may sound wasteful, but at sea, that steady power keeps movement predictable and danger manageable. Turning the engine off could save fuel briefly, yet losing time, control, or restart capability can cost far more than silence saves. So the real answer is simple. A ship avoids shutting down offshore because propulsion protects its machinery, schedule, direction, crew, and cargo. And beyond this question, the oceans hold countless engineering secrets, maritime disasters, and forgotten vessels still waiting for their stories. Subscribe to Sunken Inside for new ship knowledge, true maritime mysteries, and powerful stories about sunken vessels hidden beneath the sea.